all the love and all the wishes from Kolkata, and hope that we can meet soon in person. The stage is all yours, Shreya.
Thank you, Nilanjana, and thank you so much for that kind introduction. And thank you, Ishri Kolkata, for inviting me for this seminar. Calcutta always has a special place in my heart because I'm born and brought up there. So it's definitely a pleasure to be here today. I'll just share my screen. Are you able to view my screen?
Yes, absolutely fine.
Perfect. So today the topic that I'll be speaking on is computational fluid dynamics for built environment. So to understand computational fluid dynamics, we need to understand what is fluid dynamics. Fluid is anything which deforms under a continuous external force. My apologies. So it could be water, it could be air, it could be blood, it could be anything which deforms under an external force. And dynamics is anything which is continuously in motion. So what we are looking at specifically in HVAC is air motion. So in our case, fluid would be air, and we are studying how it is dynamically moving around in our domain. Now to understand fluid dynamics, when it had first started out, when the first code was written, the computing power was not as what it is today. So initially we would have panels and panels of servers with lots and lots of cores to run a very small problem. Now it has come to a point where we can run a much complex problem just on a desktop by using cloud computing. So you could have multiple cores that you can utilize in the cloud and not have panels and panels of servers to actually simulate your problem. So today we will be looking at the basics of computational fluid dynamics, what it encompasses in terms of the equations behind it, how it is applied to the system, and how you would run the system to understand how the process is behaving, and how you would then use that solution to rectify your problem and optimize the solution that you would want out of it. So back in the day, before computational simulations were used to study airflow around a building, what used to be done is called hot smoke testing. Once the building is completed, people would bring in a canister of hot smoke, and the smoke would be then released in the environment. Now, what would happen is, if there is any kind of zones where the smoke is accumulating, or where there is low visibility, or where there is a stagnation of air, you would understand by that movement of hot smoke. There are disadvantages to this process. One, that it can only be done after completion of the project. So it would only be possible to do it once the structure is already in place. And second, if there are any flaws that is identified by this particular testing, then it can the rectification of it would be very expensive, because you would need to do structural changes after the completion. So because of these disadvantages, there were a lot of problems with hot smoke testing. Now, computational fluid dynamics gives you the same test, but you do it virtually on a system where you can put in your boundary conditions, which basically means that you can simulate airflow around the system in terms of the CFM through a air conditioner, or a heat being added into the system or being taken out of a system, and you can see how the system is then behaving. In this particular simulation is for a dentist chair, where you see the aerosols being flying around the system. There is an air purifier at the edge of the room, and there is a air conditioning system which is on. And you can see that the aerosols which are starting to move around is being sucked into the air purifier and is removed from the system. So these are certain things that you can do to understand fluid flow and how it is working. So why would you want to do computational fluid dynamics? You would want to do it to test your design. It reduces physical prototyping because you can test a design while it is on design stage. It doesn't require the structure to be completely erected and finished to actually understand how the system is behaving. And once you've done that, if there are any flaws that you do see in the system, you can rectify it right on the design stage itself without having to do any physical prototyping. So you reduce the time investment, you minimize failures, and you reduce costs by employing computational fluid dynamics. I'll take you through the process of CFD. There are 3 stages that we see in when we talk about the process of CFD. They are pre-processing, the simulation stage, and then post-processing. So pre-processing requires the geometry, the meshing, and the boundary conditions. So I'll briefly speak about each stage to give you an idea of how the simulation is performed. So what we begin with is the 2D CAD model. Generally, what we receive is the 2D CAD model. It's very rare that you would receive a 3D model because that also requires a lot of time investment and it's rarely available. So what we receive is the 2D CAD model. This is then converted into a 2D CFD model. So in this case, this is a car park with ramps on 2 sides with some fresh air cutouts which are marked in blue. There are some jet fans which have been applied to the system, some fresh air fans and exhaust fans placed here. I will not go into details of this particular example. We'll be looking at those later, but just to give you an idea of how the process is set up. So once we complete the 2D CFD model, we convert it into a 3D CFD model to get a 3D model. Now, whatever is bounded within this wall, whatever is our area of interest is called the domain. This is the CFD domain within which the simulation will be taking place. Once we complete the geometry, and the geometry is usually the most time-consuming, tedious process because it does require a lot of fine work around the model. The next stage is defining the boundary conditions. Now, what we mean by boundary conditions is any initial conditions to the system. So anything which is forcing the air through the system, or anything which is contributing to the air movement or the heat in the system. So in this case, it could be the HVAC equipment. So it could be, say, the audio outlet or air conditioning in a room, or it could be a jet fan, exhaust fan system within the basement car park. So anything which is basically moving the air mechanically through the system is the part of the boundary conditions. The second is the heat load data. If you're doing a thermal analysis, the heat load data would be critical. So in terms of what is the heat being generated within the system due to solar radiation, due to equipment, due to lighting, due to the people, all of that would then be considered as the boundary condition. So this is typically a heat load chart that we would receive and would then apply the heat for the room, the sensible heat and the latent heat in the room to the system as boundary condition. The third boundary condition that can be considered is fire design. Now, for a fire simulation, we would want to consider a proper fire design. And by that, I mean that we want to consider a proper fire load, which is as per the consideration for the system, the fire growth curve and the fire material and reaction time as per what we want to consider in the system. So the fire load is the potential size and severity of fire, and it is defined as the weight of combustible contents per unit floor area. The fire material and reaction time could be, say, foam, fabric, rubber, metal, and the reaction time would be polyurethane or methane, nylon, propylene. And the fire growth curve basically comprises of 4 stages. ignition, fully developed, and decay, where you have the start of the fire. It has an alpha G, the growth rate of the fire, where it settles down to a fully developed um, plateau. And once the fuel is somewhat depleted, it starts to decay, which is defined by alpha D, which is the decay rate of the fire. So this is called the T-square fire curve, and it is defined by NFPA. And you can get the values for alpha G and alpha D from NFPA to define a proper fire growth curve. And how you can utilize that is if you look at NFPA or any relevant data online, you can find that your fire design can be described by the Qmax, which is the peak heat release rate, your T end, which is the end time for the fire, decay time, the time at which the fire peaks, and the time at which the fire starts. So, and you can find your alpha G and alpha D, which is the growth rate of the fire and the decay rate of the fire. And if you were to look at one particular item on fire, say for instance, chair 13. For chair 13, you would have a maximum release rate, heat release rate of 874.2 kilowatt, which is in the previous slide. 874.2 kilowatt. And you would consider the fire material as wood frame, urethane foam, quilted cotton, polyurethane, polyester batting with a polyurethane reaction. The growth parameter is 0.025, and the decay parameter is 0.009714. What that dictates is the how the fire would grow, decay, and how it would behave. So in this particular case, it would reach the peak heat release rate at 187 seconds. It would start to decay at 200 seconds, and then the fire would end by 500 seconds. So in case you want to look at a fire scenario, say in a hotel lobby or in a apartment, you would consider a chair on fire with these particular fire design components. Likewise, you can find the fire design for a car. For a car with a full tank of fuel, we consider a maximum heat release rate of 4,000 kilowatt, that's 4 megawatt. The fire material and reaction time considered is flammable fuel, metal, plastic, carbon fiber, resin with a polyurethane reaction. The growth parameter is taken as 0.188 and the decay parameter is 0.064. And likewise, we can then derive the fire curve with the peak happening at 146 seconds. By 950 seconds, the fuel is depleted and the fire decays by 1200 seconds. So these are part of the fire design that you would consider for a fire simulation. And lastly, to define the boundary conditions, the ambient conditions are very important. So if you were to look at the ASHRAE climatic design data for, say, any location, in this case, it's for Bangalore, you can find the weather conditions for the coldest month, hottest month, the extreme weather conditions for n equals to 5, 10, 20, 50 years, and the individual weather conditions for the individual months. So these can then be utilized to form the boundary conditions for the system. So in case if you have, if you want to consider wind for a particular simulation, you would see that the mean wind speed for the hottest month is 1.4 meters per second. And the principal coinciding wind direction for that particular month is 90 degrees, which is east. Is it? Yeah, east. So you can then consider these values as the starting point for your ambient conditions. So once you've defined the boundary conditions, like I was going through the process, the first stage is the geometry, then defining the boundary condition, and then the next stage is meshing. What that basically means is that within the domain, we break up the domain into millions of small cells, for which each each cell we would be calculating the data, the parameter that we are looking at. So what that basically means is that the method that is utilized for doing the simulation is called finite volume method, where it considers the domain to be broken into millions of cells. You would calculate, say, for instance, in this cell, you would calculate the value of velocity, temperature, pressure, any details that you want to CO in case of basement. And then you would proceed to the next cell. It's a time iterative method, which basically means that for this control volume, say for this volume, you would have a edge, a face, a node, a cell, and you would have the computational node for which every control volume and every node, you would be calculating those parameters moving ahead in time. Just to give you an idea of how that is performed. So for instance, for time equals to n plus x seconds, we would calculate all the values for this cell. And for the same time, we would calculate all the same values for the fluid moving ahead in these cells. And forward to completely calculate all the values for those for each and every cell for that time period. Now, once it is done, say for t equals to 0.05 seconds, it would then go on to the next time step, which is t equals to 0.05 plus 0.05 seconds, which is t equals to 0.1 seconds. And it would again restart the process, but it would take the initial value from the time step of the earlier iteration. So now the initial conditions which we had first set as boundary conditions, it has moved forward in time, and that has now become the initial conditions for the next time step. And then we would again do the entire iteration. And again, for the next time step, which is t equals to 0.015 seconds, once this time step is completed, this would now become the initial conditions for the time step moving forward. And this process is repeated until we receive a steady state condition. Now, the second part of the simulation, which is the actual turbulence modeling and the simulation, is done by solving mathematical equations of continuity for mass, momentum, energy, and species. And this is done by using the finite volume method that I just explained. It uses the K epsilon turbulence modeling, and it performs the simulation in a time variant transient analysis. The simulation used is the large eddy simulation in this case. So you do have various types of simulations like RANS, DNS, LES, but the most popular one, which is used commercially, is the large eddy simulation. And the last part of the process is post-processing, where you would extract the data from the results from your simulation, and then you have images to actually understand how the flow is moving around, whether there are any stagnation zones, whether there is any recirculation zones that need to be looked at, or any hotspots. So that is a part of post-processing. So in this case, we have velocity contours in plan view. For velocity from 0 to 1, and we can see the flow moving around the system and no flow stagnation in the system. Now, before I move into the examples, I would like to speak about the behavior of airflow that we keep in mind while designing any system. There is typically three behavior of airflow that I like to speak about. The first is path of least resistance, which means that airflow will always take the path of least resistance, even if there is opening on both sides. If this side of the path is restricted in some way, it will choose the path which has least amount of resistance. The second is that airflow will always choose the shortest route. What that means is if you have a system and say there is an exhaust fan at this corner, you have provided cutout for fresh air on this side and this side. Maximum amount of air will be pulled in from the cutout which is provided closest to the fan. It will pull in very little air from this side because the airflow will always choose the shortest route. And third is that hot air always rises. So for any thermal analysis, you would expect the hot air to rise and settle towards the ceiling. I'll just go through some case studies to show how you can utilize CFD for built environment and how you can use it to understand the problem and to rectify it and to have an optimum solution right at the design stage without having to do any structural changes. So the first case study that I'll go through is the airflow analysis. In this case, we have a 2D CAD model of car park of 21,500 square meter, which has been converted into a 2D CFD model and then into a 3D CFD model. Now, what you see in blue are the 8 fresh air cutouts. And we have 16 exhaust fans located around the system, 8 in normal mode and 8 in fire mode. Now, the motive of this study is to understand the natural airflow path. That's the first thing that we want to do. The second is if there is any kind of stagnation happening around the system, then we want to reduce that by putting jet fans and having flow forced through that stagnation zone and reducing the same. So in this case, we have the top images are for without jet fans. The bottom images are for with 24 jet fans. So if you see, we have in the without jet fan system, we have a good amount of air moving through the system from the fresh air cutouts into the exhaust. So you can understand that the natural airflow path being formed is quite evident from these images. And then you can also see that there are some zones which are not very well ventilated. So it's on the bluer side. So blue would mean anywhere below 0.1 is where we would want to see the flow stagnation and to rectify it. And bottom is where we have 24 jet fans. Now, the placement of jet fans are also very critical. You want to maintain the airflow path so that you're utilizing the natural airflow path. You want to place the jet fans in a manner that they are not contradicting with the natural airflow path. Otherwise, the effect of the jet fans would nullify. And you want to move the air optimally around the system. Now, like I said, if you're studying stagnation of air, you can reduce the scale to 0.1 meters per second. So anything under 0.05 meters per second is what we would consider as underventilated, and anything at 0 is what we would consider as stagnant. So in this case, if you look at the image without jet fans, we can see that 50% of the basement is underventilated and 25% has stagnant air, which has been now reduced with the 24 jet fans. Similarly, if we look at ceiling height, we can see that placing the 24 jet fans, you can see the direction of the fans, the placement of the fans, and how the airflow is behaving to optimize the system. So you have the 24 jet fans in the bottom image, and you can see the red color to show the jet fan movement, air movement. And similarly, if we look at the scale from 0 to 0.1 meters per second, we can see that the underventilated zones have now reduced and stagnant zone is completely reduced. So we have optimized the airflow around the system. This is the first part of a basement car park. If we consider CO and fire as part 2 and 3, This basically helps us to locate the jet fans around the system in the most optimal manner to reduce the air stagnation. Now going into part 2, which is CO analysis. Again, we start with a 2D CAD model, which is converted into a 2D CFD model. This is a car park of 2,500 square meter area. And there are 15 jet fans located around the car park. The fresh air is considered through the ramp, and there are 2 fans provided, one in normal mode and one in fire mode, exhaust fans. Now, the CO generation, this is from ASHRAE and is also there in the ISHRAE handbook. The CO generation considers hot engine emission and cold engine emission. So we take an average of both, and we take 10% active cars. Now, for a space which has a lot of car movement, say for a cricket stadium or other facilities like that, we can take an operating level of 15 to 20%. But for a general commercial space, we take about 10% active cars. And in this case, there are 94 vehicles. We can calculate the rate of CO production, which when divided by the area of car park, we can get the mass flux of CO. Now, this particular number is what we put into the system as a boundary condition. So we need to study how the system will behave for a 1 hour CO exposure. So again, we start with the velocity profile with and without jet fans. Without jet fans, we can see that there are certain zones which have very low air movement. With jet fans, we have rectified that problem. So the 15 fans are placed around the system. So if you see now that this bottom zone is quite underventilated, and there are some stagnant zones in this area. And in the case with the jet fans, we have eliminated that stagnation zone. How that would affect the CO is that when we do a 1 hour exposure, we see how the CO builds up over 20, 40, and 60 minutes. So for a 20-minute slide, we can see that the CO has started to increase in this area. It has gone up to 130 ppm. In this case, the CO is somewhere around 70 ppm. Now, again, there is a buildup of CO in this area. Although the CO is somewhat building up here, but it is starting to stabilize. And by 60 minutes, this is still unsteady, this is still unstable, and there is the CO is still building up in this area, whereas this area has completely stabilized, and the CO around the system is within our required acceptance criteria. So what we consider as acceptance criteria is 35 ppm average for a 1 hour exposure with a peak of 120 ppm. So if we were to look at the average CO concentration in the car park, we would see that for a 1 hour exposure, which is 3,600 seconds, the case with the jet fans have now settled to about 24 ppm average around the car park. And with no jet fans, the trend is still increasing. It has still not stabilized. It has still not come to a steady state. And it is moving towards moving beyond 35 ppm. Now, what I mean by steady state and unsteady state is that the amount of CO flux which is being injected into the system with jet fans, that amount is being taken out of the system in a comparative manner. In this case, the amount which is being inserted into the system is higher than the amount which is being taken out of the system. So we do not have a stable condition, and the CO is still in an increasing trend. So we have managed to bring that down. So you can utilize CFD to understand how a system is behaving, and to see which areas are underventilated or stagnant or has a CO accumulation, and you can then place your jet fans or your other means of providing airflow to disrupt that particular zone and to have a more uniform distribution of air through the system. The third part of a basement car park is fire analysis, where we consider so in this case, we have again 2D CAD model converted into a 2D CFD model. This is a car park of almost 11,000 square meter area, and converted into a 3D CFD model. Now, the fresh air is provided through the shaft here. There are two exhaust shafts provided at this end and this end. This shaft has almost 113,000 CFM of air being pulled into it in fire mode. This shaft also has about 2 lakh CFM of air being pulled in, and there are 35 jet fans which are located around the system. So all fans are working in fire mode. As for boundary conditions, the ACPH provided for fire simulation is 12. The recommended fire size, like we spoke earlier, on earlier, is 4 megawatt, 1 car on fire. The recommended fire area is 2 meter by 5 meter. The reaction type is polyurethane. We consider a duration of 20 minutes for fire. And the design criteria, again, the temperature should not exceed 60 degrees. The visibility should be greater than 10 meters at 10 meters upstream of the design fire at 20 minutes. And the visibility should be greater than 10 meters in all escape routes. Most of these boundary conditions are from either NBC, ASHRAE, or Qatar Civil Defense, Singapore Civil Defense, and from British standards for fire design. Now, to see how the system is behaving with and without jet fans, again, we have the fresh air shaft located here. There is an exhaust shaft located directly opposite to it, and there is an exhaust shaft located here. And we have 35 jet fans placed around the system. Now, in this case, what happens is that because this fresh air shaft is directly opposite this exhaust shaft, the entire air is being pulled directly from this end to this end. So going back to the behavior of airflow, the air will always choose the shortest route. And because of that, what happens is, because it's being pulled across from this shaft to this shaft, and this is almost 113,000 CFM of air being pulled in, it forms a wall of air. So there is very limited air movement in this area. And considering that the CFM for these jet fans are quite small compared to the CFM which is being pulled around, the wall of air is actually overpowering that those jet fans. So why that's important is, if you have a fire in this area, because of that wall of smoke being formed, wall of air being formed, very little smoke is actually being pulled into the exhaust fan. So most of it is being, the fresh air is only being pulled across the car park and into the exhaust shaft. So the smoke actually accumulates in this area. Even after 30 minutes, the smoke has remained in that area. So if you were to look at the visibility and temperature contours for the same, we can see for visibility at 5 minutes, the visibility is completely 0. And at 20 minutes, it's 0. And temperature, although it reduces by 20 minutes, it's back to ambient temperature. What happens is that the smoke remains in the system as cold smoke. Hello. So the cold smoke actually ends up reducing the visibility. Now, there are certain things that you can consider as a rework, but like I said, if you were to add more fans in this area, it would actually not help, simply because the CFM for those fans are extremely small compared to the CFM which is actually being pulled across this from this shaft into this shaft. So what we considered as a rework was putting a full height wall to divert the flow around it. so that your shortest path is not available to it anymore. How that helps is now the airflow, because it's not getting that path to move around it, has no choice but to, to move across it, has no choice but to move around it. So it has to move around and to access the exhaust across the wall. So it cannot access it directly from across the car park. And then the fans are located to make sure that the ventilation is optimal around the car park. And how that helps is, with the same fire location, you're able to move the fire into the exhaust shafts rather than being blocked by that wall of air. And you have the smoke is cleared out by 900 seconds. I'll say that again. So in case of such a problem, you can test the design again virtually rather than having to do changes, structural changes or any kind of other changes to check it again and again on site. So now if we see the visibility and the temperature contours, we have full visibility and temperature at ambient conditions by 20 minutes. So the next case study that I'll be going through is for air conditioning. So in this case, we have a school auditorium where there is the stage side and the hall side, and both the sides have been provided with individual supply and exhaust system. So for the hall side, there are 4 ducts for supply which have been provided with multiple supply grills dropping down at this false ceiling height. And there are return risers which are provided at the side and the back of the hall for return air. And for the stage side, there is a continuous return air grill provided at the back of the stage. And on either side, there are 5+5, 10 supply nozzles provided. And all supply grills are provided at 18 degrees centigrade for air conditioning. So for air conditioning, the boundary conditions we need to consider is the heat load data for that particular space. So for instance, in this case, we have the hall area and the stage area, and we have to consider the latent and sensible heat for the load of people, the roof heat, the ceiling heat, the wall partition lighting load, all the loads that we need to consider for the system. These are then applied to the system to study how it's behaving. Now, there are 2 strategies that we had to study in this case. So if you see, these are the supply grills that are coming down at the false ceiling level. And then for ventilation strategy 1, there are return air risers which are provided at the side of the hall, and there are 2 which is provided at the back of the hall. And in the second strategy, a boxing was provided for the return air riser, and the number of return air risers were increased at the back of the hall. So earlier it was 2, then it was increased to 5. Sorry, return air grills were increased to 5 at the back of the hall. And there was the CFM, supply CFM was increased for the 4 ducts. Why that was done is that for strategy 1, because there were only 2 return air risers provided at the back of the hall, you can see that the heat is accumulating at the back of the hall. So we want the room design temperature was 23 degrees plus minus 1. In this case, we see that at the back of the hall, there is a peak temperature of 27.5 degrees. Whereas in strategy 2, once the supply CFM was increased and the number of risers were increased at the back of the hall, the peak temperature is now around 24 degrees. The other thing to notice is that although the supply temperature is at 18 degrees centigrade, by the time it actually reaches, say, 1.5 meter height, it is somewhere around 21 to 22 degrees centigrade. So there is the heat is moving to the back of the hall. Now, if we were to look at average temperature for the hall area is for strategy 1 is 24.6 degrees centigrade. For strategy 2 is 23.3. So it has decreased by 1.3 degrees. And the stage area, although because we have not changed any strategy in the stage area, is somewhere around 22.4 to 22.8 degrees. So you can utilize CFD to understand if there is any heat accumulation happening, and if there are any zones which you have detected as hotspots, you can rectify the problem by either providing a more CFM of supply, or by providing more return air risers, or any sort of system to remove the hotspots. The next case study is for a factory airflow and comfort analysis, where we have a factory with some equipment over here, which is radiating heat. There is a paint shop over here, which has 2 ovens, which is radiating heat. There are some fresh air openings provided on all 4 sides. There are some open doors on this side, some louvers provided on this side and this side. And again, we have considered 2 ventilation strategies. One is that the exhaust fans are placed on this end of the factory, opposite to the equipment, with some fans placed in the center to propel the air from this end to this end. And in the second strategy, it was exactly opposite, where the exhaust fans were provided on this end of the factory, with air being propelled from this end to this end. The objective was to maintain average temperature at 39 degrees. So we have an ambient of 39, and we want to have minimum delta T, which is to be considered for the system. A west wind of 2 meters per second has been assumed. So in case of strategy 1, we see that because the air has to travel from this end to this end, this is where the exhaust fans are placed, the heat is also being carried through the factory to this end to be exhausted out. So what you see is a much larger increase in delta T for this strategy. Whereas in this case, because the air is moving from this end to this end, with exhaust fans placed over here, right above the heat radiating equipment, all the heat which is actually being radiated is now pulled upwards and outwards from this end itself. So for strategy 1, we have a delta T of 2.04 degrees C. And for strategy 2, we have a delta T of 0.57 degrees C. And this is what we wanted to maintain, a minimum delta T for this particular scenario. The next is a data center analysis, where a data center is considered with a hot aisle containment. The hot aisle is then connected to a hot return air duct, and then back into the pack unit. Now, there is one small room over here and one big room over here, and we want to study the cold air is a free discharge into the room, and we want to study the inlet temperature for the server racks. So in this case, the boundary conditions could be the hot air containment, cold aisle containment, hot aisle containment, cold aisle containment, the flow rate per pack unit, the supply air grill size, the supply air temperature, the return air grill size, number of standby units to be considered, the number of racks, heat generated per rack, air leakage percentage, the hot aisle return duct material, if that needs to be considered. If there is a false floor, in case it's a raised floor, we would then consider the perforation or the grill size that has been provided in front of the racks. So in this case, we can see the velocity of air moving around the system at 1.5 meter height. So what you see in between are the hot aisle, and there is a free discharge of air into the cold air into the room. And this is the temperature at 1.5 meter height. So the cooler air is moving around the room with the hot air being pushed into the the hot aisle containment. So in this case, the supply temperature is at 21.5 degrees, and the highest inlet temperature recorded is 22.7 degrees, and the highest outlet temperature recorded is 32.7 degrees. If you were to see the results in a sectional plane, we can see that these are the server racks. This is the return air duct that is coming around the room. This is the hot aisle containment with the return air duct placed right above it. And we can likewise study whether the server racks are getting the cool air that has been provided in the room. The next case study that I'll briefly talk about is the DG set delta T and airflow analysis, where you have a DG room with, I think, 12 number of DG sets placed in the room. With for each DG set, 2 ventilation fans have been provided to for cooling the room, cooling the DG set. In this case, the radiator side of it, the radiator outflow temperature, air outflow is at the back of the room, and what has been considered is a shaft which is right above it with the air inlet provided on the same side. Now, this could cause short cycling of hot air from the radiator end into the inlet, air inlet, which could then be carried in by the ventilation fans and could increase the temperature within the room. So it is critical to study what delta T is being formed inside the room. So in case of a DG analysis, the boundary conditions that you would consider is the skin temperature of DG, the heat radiated from the engine, heat radiated from the alternator, amount of combustion air, capacity of DG mounted radiator fan, radiator airflow outlet temperature, skin temperature of insulated exhaust pipe, number of ventilation fans, the capacity of each ventilation fans, lower intake air, lowers for intake air with percentage opening, and the ambient conditions. Now, apart from that, there could be other boundary conditions that you can also consider, like the attenuator, the pressure drop across it, whether the pressure within the room is staying as per requirement. So those are also something that can be studied. So in this case, if we look at the results for velocity profile, we see that the air is moving into the room. So the intake air from the louvers right above it is being pulled into the shaft through the ventilation fans and into the room, which then goes above around the DG body and is sucked in by the radiator fan and then out again. And there could be some amount of short cycling happening because of the because the inlet and the outlet is on the same side. So if we were to look at the temperature profile for the same, we see that the hot air being pushed out from the radiator end is somewhat being short cycled into the room through the ventilation fans. And because you would expect that the central DGs would have most amount of short cycling of hot air happening, there would be some amount of increase in temperature in the central part of the room. So we see like for the central part of the room, the peak temperature is somewhere around 44.5 degrees for an ambient of 41.3, and we have a delta T of 3.18 degrees. So you can study even for equipments how the system is behaving. The last case study that I'll quickly speak about is the audio analysis, where we have ODUs stacked for a high rise, for every floor of a high rise, and we want to study how the thermal stack effect is being created and how it's affecting the ODUs on every floor. So what happens is if you stack the ODUs in a dedicated ODU shaft, without wind condition, the upward draft, the upward movement of hot air will create a stack effect, which would then have a sort of an upward movement of air within the shaft. So in this case, we have about 57 floors of an high-rise building with 49 typical floors and 8 refuge floors. A total of 1776 ODUs are placed in 23 dedicated shafts. So again, in terms of boundary conditions, we have the capacity of ODUs, the operating ambient temperature, dimension of the ODU, the fan air quantity, the fan exhaust air temperature, the ambient conditions to be considered, and the average wind velocity if we need to consider, and the coincident wind direction if need to be considered. So if we quickly look at the results, we see that in a without wind scenario, whatever velocity is being formed is because of the updraft of the hot air from one ODU to the other in that particular ODU shaft. So this is called the thermal stack effect, where the hot air, because it naturally rises, creates an updraft within the shaft itself. So although there is a no wind situation, we see at the top of the building, we have a velocity of 3.5, peak velocity of 3.5 being formed. Now, that also means that the heat is moving upwards and is enveloping the building as it moves upwards. So what that means is, if you look at the first floor, we have the velocity moving outwards and upwards, and the temperature moving outwards and upwards. So in this case, we have an ambient of 35.8 degrees with a peak of 41 degrees. And once we move upwards to the 21st floor, from the first floor where the peak velocity was 1 meters per second. Now on the 21st floor, we have a peak velocity of 2.5 meters per second due to stack effect. And we have a peak temperature of 43 degrees. We want to study the inlet temperature of each ODU to make sure that the inlet temperature does not go beyond the operating range. For some ODUs, it's 48 degrees. For some ODUs, it's 52 degrees. So we want to keep that within that particular operating range. And if you look at a refuge of a higher flow, again, this is all the flow being created because of the ODUs only, and with a peak velocity of 3.5 meters per second. And the temperature is also now moving upwards and outwards. There are certain things that you can observe, which is, so for a refuge balcony on a higher flow, because of the heat accumulation, the for an ambient of 35.9 degrees, we have a temperature of around 38 degrees on the refuge balcony. And because of some ODUs facing in a certain direction, some balconies can also feel a higher temperature than the ambient. So for the top floor, 52nd floor, if you were to consider that, that is the flow which is enveloping the building, which is purely due to the ODU heat. And the heat from the ODUs are now peak at 43 degrees. So we see a peak velocity of 3.5 meters per second at the top of the building, with a peak inlet temperature recorded at 41.1 degrees centigrade. The refuge balconies have a 2 degree higher temperature than ambient, and some balconies on this side have a temperature of 3 degrees higher than ambient. So if you want to consider, if you want to change the direction just to make sure that those balconies are not heated, or if you want to, if the peak in the temperature is not within the operating range, you can understand that dynamics and you can rectify it while it's still being designed. So just to summarize the entire presentation, computer simulations offer an exciting opportunity for validating aspects of ventilation, smoke movement, natural airflow, and thermal comfort right at the design stage in accordance to safety standards and guidelines, and can significantly contribute to an efficient building design. It provides the construction industry with an opportunity to obtain an assurance on effective smoke removal at an early stage when the building design is still on paper. So with using high performance computing servers, it is now possible to conduct a virtual hot smoke testing. And if any problems are identified, you can rectify it while the building is still on the design stage. So the ventilation strategy can be quickly modified and retested. This saves money and time that is required to obtain the optimized smoke ventilation design. And it does not need to be revised after completion. It can be done while it's still in the early stages of design, and gives a very good opportunity to optimize the solution even before you start construction. That's it from me. Is there any questions?
Madam, I have a question.
Yes, please, sir.
Yeah, my name is Pallav, and as a day job, I sell fans. So I'm connected with basement ventilation systems, and I get to face my customers. Every day we discuss CFD and we sell through CFD and all that. So
Right.
I have two questions basically. My first question is there any guideline in terms of the time allowed for the smoke to clear out from the basement? Because I have not come across anything, and sometimes this confusion comes.
Right.
So
unfortunately, there are no guidelines, neither in ASHRAE, neither in ASHRAE, neither in NBC, neither in NFPA. What we do consider is the visibility and temperature. Again, that is also a point of contention, because for a basement, there are no specific guidelines as such which has been put out in terms of visibility and temperature as well. So for larger spaces, it's much easier to understand, because you have that volume of the volume that is available for smoke reservoir. In case of a basement, because of the lower height, the visibility does fall sooner.
yes.
So what we consider is that at 20 minutes, not more than 1,000 square meters should be smoke logged. That is one thing that we consider. And the second thing we consider is that at 20 minutes, the visibility should be greater than 10 meters. Now, again, there is no basis for these considerations, because there are no guidelines in terms of these considerations. But
what happens, ma'am, is when we talk about this, see, basically we somewhere look between 15 minutes to 25 minutes kind of. Depending, of course, on the geometry. Some geometries are very complicated. We can't improve beyond that.
Correct.
So it does happen. But sometimes when the fire officers come, especially in our neighboring countries and all that, we face this question. They ask, what is your guide? On what basis? Why not 5 minutes? Why not 6 minutes? So that kind of a question does come up. So I thought of asking you from your experience.
See, like you said, we also consider 15 to 20 minutes. Sorry, not 15 to 20 minutes, 20 to 25 to 30. Maximum 30, we would want the smoke cleared out. Now, there is another part to smoke simulation, which is called evacuation modeling. Now, what happens in that is that your smoke simulation would give you your ASET, which is the available safe evacuation time, and your evacuation modeling will give you the RSET, which is the required safe evacuation time. And then you can compare the two to see whether the amount of time that is required for evacuation, are we getting that in terms of the ASET, which is coming from the smoke simulation. Now, the problem with car parks is that although the visibility starts dropping sooner, one can argue that the occupants in a car park are not that many. Right, you wouldn't have like in terms of a office building or
absolutely, yeah. So and again, actually, we do not consider it to be part of the evacuation. We don't expect people to come there during a fire.
Correct. Yeah. So in that case, the only other thing that you would consider for a car park is then the access to the firefighters.
Absolutely, so, yes.
Right. So what we would think is that they should have good access by say 20 minutes or so. If the smoke has started to die down or it has been evacuated in a proper manner, they should have a clear access to the fire to take it out. So apart from that, unfortunately, there are no guidelines to adhere to in this particular case.
Right, ma'am.
Right.
Madam, I have a second question, which is a little different from what I asked, is that the basement. My questions are based on basement car park ventilation because that is what I do.
Absolutely, sir, please.
So now when you do a basement car park ventilation, right, from geometry, boundary conditions, meshing, simulations, modeling and all that.
Right.
Now the question that we every day ask, and I don't know why this has crept into the market in our country, is that CFD is supposed to be free. Now, is it possible actually to provide this service free?
No,
this intricate science?
No,
it
is not. It is not simply because it's a very intensive process. Like every single part of the process is very time consuming, and it could happen nowadays that, the basements are also quite big. So you do have to use a lot of cloud computing to run that simulation.
Absolutely.
So to be very honest, I don't agree with the pricing which is there in the market either. But unfortunately, I don't know why that mindset has crept in, but this process is highly technical. Even to understand, how to do it and how to present it, how to rectify the problem is very, very technical. So that is definitely something.
I think the people to be blamed is people like us who have gone ahead and done this. And
Correct.
What I tell my customers is that free CFD is no CFD. People take a 2D AutoCAD drawing, put the fans and submit it. They're actually not doing any simulation because an actual simulation takes a lot of time.
It takes a lot
sat
of time.
in front
Correct.
of computers and I've seen it takes days to complete a simulation.
Correct.
And
that
if
is
you're
absolutely
using,
correct.
if you're using a software like Fluent or something, it costs a lot of money. There's a royalty to be paid.
It is
maybe for
extremely
open
expensive.
protocol software, it's cheap, but then it cannot be free for that matter. That's what I feel.
No,
Thank you, madam.
definitely.
I thought your presentation was very good and I really enjoyed it. Thank you.
Thank you, sir. Thank you for your time. Thank you, sir.
Shreya, there is one question. In
Yes,
fact,
please.
that is, I think partly it was already discussed with Pallav. There's a question from Kaushik Maiti. Which software is used for the CFD analysis?
So as per HTTP protocol, I'm not supposed to take any names, but there are a lot of software, commercial softwares, which are available in the market and are quite good. Now, like discussed, there is ANSYS Fluent, although, it is very expensive to get an annual license as well. There are other ones also, which I feel is quite good. So there's some ambient noise. Hello?
Yeah, please mute, please.
Yes, please. So in terms of software, there's only one thing that I would like to say is that for any CFD software, your equations are pretty much the same. It's your technical, expertise that is more important. So there's a very popular saying in CFD that garbage in equals to garbage out. So it's very important that you know what you're doing for any software. I would suggest that you understand how the equations work, and the other part is that the boundary conditions are extremely important. So the more number of boundary conditions that you can apply to a system, the better it is. So you would try to get it to as close to a real scenario as possible. So you can look at other softwares. There are some open source softwares also, but the learning curve is very steep with those ones. And there are some commercial softwares as well. As far as HVAC is concerned, Fluent is one of the good ones. There is OpenFOAM. There is quite a few out there which can be utilized. But again, it is extremely important to enhance your expertise in it before you start to depend on the software.
Great. Yeah, because CFD is something, because we have seen in ASHRAE, I mean, there are a lot of distinguished lecture programs are done on that.
Right.
So it is something which is picking up in the industry, and definitely kitchen ventilation, basement ventilation, and in relation to the thermal comfort, it is very important topic nowadays.
Correct. Absolutely. It is extremely important. And I feel if someone can dedicate the time, it is something which is very interesting as a topic as well. Because it gives you the opportunity to actually solve a problem which it is very interesting. Like, I find it quite interesting to work on. So definitely, if someone wants to go into it, I would definitely suggest learning about it.
Great. There are a couple of more questions.
Yes.
There is one question. What is the minimum time required for CFD in case of a basement car park?
So again, that is dependent on the area of the car park. So if the area is very big, then it could go into 10 days, 15 days. If the area is much smaller, we can complete it within like 3 to 4 days. So again, it depends on the number of, it depends on the area. And then it depends on the number of cells that we are breaking the domain into. So that is also the other aspect of understanding timelines.
Great. There is a couple of requests by some of the participants regarding your presentation. I think you can get it from Kolkata chapter of Shreya, so because it has been, I see it is recorded, so you can get a view. But otherwise, you can note down the number for very specific question or very specific issue. You can send a mail also to Shreya.
Yes, please.
She'll be too pleased to.
Absolutely. Please, you can direct any emails towards me and I will be happy to answer.
There's one more question. Can we perform a CFD analysis without knowing the outlet temperatures?
Outlet temperature of a specific equipment? What are we talking about?
Yeah, I presume so.
Okay. See, outlet temperature is critical because obviously if there is any kind of short cycling happening in the system, we would want to know what is the outlet temperature of that particular equipment. So say in case of a DG set or a chiller or anything which is throwing out heat into the ambient, it can get sucked back into the equipment because of short cycling of air. So that temperature is very critical because it could range from the ambient to anything, right? So it is a critical data to have.
There's another very interesting question. Considering auditorium scenario, if you provide supply from bottom and return from top, is it better than conventional supply?
Absolutely. I think that is a very good strategy to have, although very few people in the industry actually implement it and follow it. What happens in that case is we are disrupting, there are two things that can happen. One is that we would only have to cool down a specific height, and the second thing being that it would cool that particular height much faster. So in case of the auditorium, if we see the supply was at the ceiling level, by the time the air actually hit the floor, it was at around 21-22 degrees. So the supply from 18 was now coming to 21-22 degrees. Now, if you were to provide the supply at the bottom, we can actually throw in air at a much higher temperature to get the same effect. So we would end up getting a much better effect. Plus, we would also reduce the time it takes to cool that environment down. So it is a much better idea to have the supply on the bottom and return at the top, because you would actually be taking out the heat from the top layer and supplying the air at the bottom layer, the cool air at the bottom layer.
Just a question like how this CFD link, since it is also linked to the thermal comfort, with the present pandemic situation in the hospitals where the upgradation is being happening to make it very much suitable to the atmosphere. So how this CFD can be, or is it already modified, or the technology has been upgraded to match the situation?
So there are, what you can do, obviously with the clean room simulation and hospital kind of environment, there are air purifiers that are considered. Now with CFD, there is a possibility to actually simulate species, like any kind of small species with small ppm. Obviously, it also depends on the capability of the software to handle that. But like I was showing you for a dental clinic, if there are, say, aerosols flying around, you can study how that is being extracted from the system, and in a much efficient manner. So the the dental chair simulation that I had shown earlier was actually for a dentist, where his question was where he should put the air purifier so that the aerosols are not flying towards him but away from him and the patient and into the air purifier. So we had performed the simulation with the air purifier in different locations of that chamber, of the dental chamber. And we found the optimum location where it's being removed from the system in a much efficient manner, and without having, without moving towards the dentist or the other assistant in the room. So these things can be performed keeping something like that in mind. Yes.
Great, great. And one more question: how can you visualize smoke propagation in an underground garage and test the ventilation system?
Is that related to basement car park, the smoke simulation that?
Yes.
So in terms of visualization is exactly how I showed you the smoke simulation movies, where you can see how the smoke is moving in the system, or whether it's not moving in the system due to some stagnation or recirculation zones being formed. And the other way to visualize it is by the visibility and the temperature contours, to see whether if there is any smoke accumulation happening in the system, then the visibility will drop in that particular zone. So those are certain tools that you can use to understand smoke in that system.
How will you test the ventilation effectiveness?
Sorry, sir?
How will you actually know the ventilation system is effective?
So again, like I showed in the example, that when that ventilation system failed, because the air was moving from so if I were to go back to that, this was testing the ventilation system. We found that the smoke was remaining in this zone. The smoke is in black. And because it is not getting pulled into the exhaust shafts are pulling in fresh air completely. The smoke is remaining even after 30 minutes. So you see that timer over here. This is in seconds. So by 30 minutes, now it's past 20, 25, and now 30. So even at 30 minutes, this smoke is accumulating over here. So that is testing the ventilation system. And once you rectify it, you can again test it to see how, with this timer, how the smoke is moving around and whether your system is now evacuating that smoke as you would intend it to. Does that answer the question?
Yeah.
Okay, yes.
And is there any example, or you are aware of a cooling tower CFD simulation?
Cooling tower, we've not performed, but for any simulation, the critical thing is the boundary conditions and the geometry. So, if these things are available, then definitely it can be done.
Awesome. Okay, thank you, Shreya, for this very interesting presentation. And a success of a presentation is actually understood when the number of questions increase.
Right.
So there is always a shyness for the first question. The moment the first question starts, as Pallav did today, that
right.
says the motion, and we had questions.
I'm glad.
It's really a very good presentation. It's appropriate to the topic, because I have heard such presentation in Ashraf platform for the CFD.
Right.
And maybe for the first time I heard such a voluminous presentation by you. Lovely presentation.
Thank you, sir.
And very nicely presented, and everybody could understand. And you have the pictorial way, the movement, the slides, the smoke moving, that actually makes the people understanding very, very clearly.
Right.
Thank you very much for making the presentation, and we look forward definitely in future also to have, as Nilanjana said, more interactions.
Absolutely.
So Amitava, can you please?
Thank you, sir. Thank you, ma'am. Now it's time for the vote of thanks. Officially, ISRE Kolkata chapter is very much thanks for the presentation. Now I would like to call Mr. S.N. Bose, sir, for the vote of thanks. Bose, sir, please.
Yeah, on behalf of ISRE Kolkata chapter, I really thank the presentation made. And although I don't understand much the subject, but really enjoyed thoroughly. because of the lively and very informative presentation. Thank you very much once again.
Thank you,
Thanks.
sir. Thank you, sir. Thank you everyone for attending this webinar, and it's been an absolute pleasure. Thank you so much.
Thanks.
Thank you.
Thank you.